But let's see. The only people who will be allowed to sleep will probably be my two kids. The rest of you should probably try and stay awake. What I want to do today is talk about evaluation of low carbon buildings in communities and look at that in some detail. I think we are probably beyond the point where we say, we should design sustainably, we should build sustainably. We have to. I don't think there's a choice. But how much do we evaluate the performance? That's why I've called it how far, how much. What I want to do in the lecture is talk a little bit about our group. There's a lot of information in the refreshment area about our group, so you can find that, but just to give a flavor of OISD and our group. A little bit of background, linking climate change, energy use and buildings. Just lay out some research challenges within which we operate now and give some insights from our own research projects that we've been leading over the last few years. And then some final thoughts for future challenges and research. So moving on to the Institute, quite a few familiar faces, quite a few people here who are from OISD. So I don't have to talk too much, but essentially to say I am based in OISD, I'm part of that as well. This is the university's flagship multi-disciplinary research institution, which brings together architecture, planning, real estate, and construction. So it was about 10 years back almost that it was formed as an institute. And in 2008, it was a hefty report that was brought out, regarded it as one of the UK's largest institute. We are involved in most of the Research Council programs, whether it's sustainable urban environments, 1, 2, and 3 phases, energy research programs, living with environmental change, and also now lifelong and health and well-being. A lot of information is there on the website, so I'm not going to go into lots here, but you will probably find something about sustainability at all scales, within the institute. The institute has about 8 research groups, so it operates in terms of the intellectual leadership happens through the research groups, one of which is the low carbon building, which is my group. And our portfolio of work tends to get funded from ESRC, which is the Economic and Social Research Council, EPSRC, TSP, industry, and also international agencies. We have quite a few projects at any given time. We'll have about plus 20 projects going on. We also run a sustainable building program, and we've had a few awards as well. So I'm going to talk not about all the projects. It'll probably take me 3 days to just tell you about the projects, but just pick up a few things. Now, before I start, just to confirm that one of the things I want to do is give an overview of the issues. I may not talk about everything, but if there are questions, feel free to ask me about things that I don't talk about as well. Now, as you know, over the last 6 months, I'm sure it has hit you in some way or the other because the press has covered this quite a bit. The Intergovernmental Panel on Climate Change has released 3 reports over the last 6 months. The 5th report came out in September last year, which reaffirmed that climate change is happening. Greenhouse gas emissions are coming from human activities, which is the dominant cause. The second report that came out last month reconfirmed that it is severe and irreversible impacts will occur if action was not taken or is not taken now. And the third report, which came out almost last week, actually said something which I think is quite amazing. It is actually saying that it is possible to still stay within 2-degree limit, whereas many researchers around the world are saying we are beyond runaway global warming. We are beyond the time when we can return back to where we were. But what it says, it requires a wide range of changes, and the changes that it's talking about are, I think, quite wide-ranging because it's talking about technology, institutions, and most difficult behaviors. Very challenging to do. And it's saying that efforts to reduce emissions need to take place from at all sectors, including energy. So energy efficiency, renewables have a renewed interest. I'll let you look at it for a second, but essentially I've downloaded it yesterday, looking at what the CO2 levels are as of now. And I was surprised myself. It's actually close to 400. When I started to teach, it was 391, I remember. When I did my PhD, it was 383. So it has phenomenally increased. It increases to about 2 to 3 parts per million. Now, James Hansen, one of the leading climate change scientists, used to say that if we are beyond 350 parts per million, we are in the danger zone. So we are already in the danger zone. We have to reduce substantially. The lecture is not about this. The whole lecture could be just about, stabilizing carbon emissions and reducing it. But the point is that this is the principal cause. The point is also that climate change will affect everyone, actually. It doesn't mean, it will affect only a few people, whether it's heat stress, drought, flooding, or extreme events. The scale of and intensity of impact will probably depend where you are. And the failure to act could result in significant impacts to people and places. So, it is a given now this is going to happen, but adaptation is not a substitute for mitigation. We have to do both. In this lecture, I'm going to actually focus just on mitigation, not that much on adaptation. But if there are questions on adaptation and resilience, I'm happy to take those, given that we've done research. Now, this is a slide you might have seen in many lectures. I think Sue and I probably started using it 10 years back. And these kind of impacts were felt that time. You would get flooding and other things. And then the 2003 heat wave occurred. And as you know, after that, something which we call as excess summer deaths was coined as a term. And in this country, we get about 2,000 summer deaths. And this is, this kind of a summer in the current climate science confirms that this will become regular. So we have to be prepared to live in homes which are warm in summer, but also, cool in, or warm in winters and, cool in summers as well. Now again, but why are we talking about all this? We're talking about all this because buildings are a large part of the problem. This could be anywhere. This is actually Beijing in China, but it's. And the reason is, if you look at the global building sector, 40% of energy use happens because of energy used inside buildings, because of things that we do in buildings. Buildings consume about 60% of world's electricity. About a third of global greenhouse gas emissions happen because of things in buildings. 30% of materials, whether you talk about resource consumption or waste generation. So the point is, whichever angle you look at buildings from, building sector is very important globally. And to be honest, the United Nations recognized it in their last report quite openly. And they said that building sector offers the low-hanging fruit. Now, I don't disagree with them, but I think one of the things you have to be careful of is, to come to this assumption straight away that reducing energy use is easy and cost-effective, because it might be cost-effective, but it isn't easy. It takes time, but it's important, not just for reducing energy use, for social reasons, economic reasons, for political reasons. Now, coming back to the UK, the building sector in this country is quite significant. About 45% of energy use happens in buildings, which is responsible for the carbon emissions. This can happen either because of when we heat the buildings, or when we're using electricity. Now, within the domestic sector, which is responsible for 27% of emissions, about 3/4 happens due to space heating and water heating, and 16% because of appliances. So, building design is critical to achieving a good performance. But the point is that buildings can also change rapidly without pain, and they are in the front line for both mitigation and adaptation. We spend about 90% of our lives inside buildings, so actually adapting them for future makes complete sense. Again, you might have come across this. This is an image showing the SAP ratings of UK properties. So in the UK, we have a SAP scale, standard assessment procedure, on a scale of 1 to 100. And as per the built form, you can see that most of the stock is actually in a very poor state. The red actually is counterintuitive. It means the SAP value is high. And that's a big job. The UK housing stock is actually the poorest in Europe. So a lot of work needs to be done to improve existing housing. And there are drivers of change. Again, you may have come across this. The Climate Change Act, which requires greenhouse gas reductions by half in about 10 years, 80% by 2050, so another 35 years. And then we also have, the UK Carbon Plan, which sets, 5-year budgets for us. But interestingly, one of the things it says is that by 2050, all buildings will need to have an emissions footprint close to zero. All buildings. That means 27 million houses and 2 million non-domestic. That's a big assumption they're making. It's there in the report. You can actually read it. The domestic sector is also required to reduce emissions by about 29% by 2020. So, lots and lots of things need to be done, which is why we have quite a bit of, near legislation. The reason I call it near is because, all new homes, for instance, need to be zero carbon by 2016. All non-domestic buildings, for instance, are required to be zero carbon by 2019. The government still not defined what zero carbon exactly means. It's near zero carbon to some extent. But there is this ambition, target, aspiration, whatever we want to call it. So the building sector is, the centerpiece for a raft of legislation and a raft of government policy. And both existing and new buildings would need to be improved substantially. And that's where our research challenges come in. And I'm going to lay out some research challenges before I go into my projects. And first of which is the low carbon refurbishment context in itself. As you know, we have about 27 million homes. 21 million homes will be standing by 2050, which means we need to do something about those houses now. Now, the UK government, interestingly, set a target. This is under the Labour government, actually. And the reason I keep this is because I think it is interesting to look at the scale of challenge. Nearly 500,000 houses a year to be done. So if you calculate 12,500 houses a week, that's just over one per minute. It's a lot that we are looking at in terms of improving the houses. So the challenge is quite big. Now, we have to also put it in context of what people spend. On an average, people spend about 1,500 on alterations, improvements, and repairs in 2008. And that's the kind of money that people are going to spend to actually improve their houses. And we need to bear that in mind when we are designing these kind of programs. Now, one of the things that you may have come across is Green Deal, which I'm not going to talk about in terms of judgment, whether it's been successful or not. But one of the things that Green Deal does is that it has a golden rule, which is quite fundamental to its success, which says that the estimated savings on bills should be higher than or equal to the cost of repayments, which means if the savings are not as expected, then people will end up paying a lot, and it is a financial model. So there is a lot of discussion about this, which is why the issue of performance gap comes in. But what is this challenge really? We are looking at large scale, so I think it's not just about house by house. I've also always believed that if you have to do refurbishment, it's got to be whole house, because you spend a lot of effort in putting things together, putting up the scaffolding. It makes sense to do it. It also avoids something called lock-in effect. Lock-in effect is when you do unambitious improvements, so that houses are not, or buildings are not improved to their maximum or to their optimum level, and they underperform. It's got to be cost effective, and it's got to be rapid, and which is one of the reasons why my doctoral research actually looked at this, that we need to be looking at buildings in a way that we can identify the worst performing properties, let's say rapidly, and in addition to making citywide estimates. So we need a tool by which you can say these are the houses that need to be improved, at what costs, and also at a city level or a community level. But there is always a but, as you know. There's one big issue in reducing energy use in buildings, that it's a wicked problem. And as you know, wicked problems need wicked solutions. You actually can't solve wicked problems, you can manage them. And the reason why reducing energy use is a wicked problem are these three things, which quite a few people have talked about. Fergus said this, Fergus Nichols said this some years back, that there is this dynamic relationship between buildings, occupants, and climate that determines energy use in buildings. So it's not just about technical improvements. But then there is even more complication. People also, and building, climate, they all come together to use equipment to provide whatever heating, cooling, lighting in buildings. Behavior is central to it, because all of that then, works with behavior. And then the energy use itself can be determined directly by occupants. They can open the window if the heating is on or the mechanical ventilation is on. So it needs multi-disciplinary approach. You need a lot of disciplines to work together. Simply architects and engineers aren't enough. We need sociologists, psychologists, physiologists, and many others, economists, to work together, because it is a wicked problem. And it's very important to bear this in mind. I think when Steamers and Eon did it, they didn't realize actually the potential of what probably they had done. But I think this is a phenomenal advancement in our understanding of energy use in buildings. And that's why we get something called an energy performance gap, which is, some people say, an unintended consequence, but is it? Looking at the socio-technical system of buildings. Now, what is it? I'm going to talk about energy performance gap, but I think I need to define it first. It's the difference between the modeled energy use of a building, or the predicted energy use, compared to the actual energy that's recorded on utility meters. And it tends to be, several times greater, not just one or two, several times. It is because of how the building is put together or refurbished, and occupant behavior, and a number of other things. The Green Construction Board did some work recently, and they found that in non-domestic buildings, in terms of energy use, typically a non-domestic building will be using 200% more. 200%, that's a lot. If in terms of cost, 240% more. Think of the accountants who are trying to estimate how much the running costs are. And in terms of carbon, about 250%. And I think they are pretty conservative. You can actually get much worse than that. So this is beginning to come into the system now. People are beginning to notice it. Whether something is going to be done about it, we don't know. But something is being done about it in Green Deal. Actually, this came out last year, and it came out very quickly. Actually, after Green Deal came out, the government released this, which said that people have to use correction factors when they are trying to estimate energy savings. So if somebody is actually trying to calculate savings from cavity wall insulation, they have to drop the savings by 35%. Because of the performance gap, because we don't know what happens. And don't ask me why it's 35%, not 32%, because nobody knows why it's 35%. It was just seen as a convenient number. There isn't really proper science behind it. And that is why a lot of work needs to be done to actually quantify this energy performance gap. But it is beginning to be recognized. It is not something that is being ignored. And there's widespread, but how does it matter? Sometimes people ask me, okay, it's there, but why does it really matter to us, people living in houses? It does, because if you look at it, and I think Zero Carbon Hub had done some good work in this area, where one, it undermines the policy itself. So effectively, we are saying that you save virtual carbon, not real carbon, if you don't do it properly, and it's there's no feedback, and it's the building isn't followed through. It questions the role of even new housing, whether we can achieve our targets. For people, it matters because it means higher energy bills, and that of course matters. And it of course undermines buyer confidence, which, given this economic situation, is quite important. And for design and development teams, underperforming new homes will be very damaging to reputation. I think this is actually the biggest risk for many players. Big, let's say social housing providers or private developers. This could be a big risk. And a number of players have been trying to look into this, whether it's Good Homes Alliance or Zero Carbon Hub or NHBC. But a lot needs to be done in terms of building the evidence base. Now, the causes are plenty, and that's what my whole presentation is about. So I'm just going to give you a summary of the causes. The causes are not because of occupant behavior only. I think that's a myth. Occupant behavior contributes to it, but it is not necessarily the main cause. It actually starts right at the design stage because of assumptions, because of lack of proper communication between teams, because of using unskilled or semi-skilled people to build things. Big issues with commissioning, not just not commissioning properly, but the tools that are used for commissioning themselves aren't calibrated. There's no proper handover of the design intent to the user, so people don't have a clue how building is to be used. This is very, very common. Hardly a user guide. Has anybody seen a user guide for a building? See, one. And I know Mary because she works in the field, and two. Again, there's a big lack there. And then, of course, there are issues with the in-use stage and occupant behavior. But before we come to behavior, there are a lot of things in the chain, and that's what we've been trying to study. Now, the other thing we can't ignore while we look at reducing energy use and the rest of it is about adaptation, resilience, and other things. And one of the key things that comes in is overheating. We did a project on climate change adaptation for suburban neighborhoods, and we would ask people in Delphi groups and focus groups about drought, flooding, and overheating, and damage because of storm. And people would always tell us, or most of the times, that we can see water or we can't see water, so we can do something about it. We can't see heat. And that's quite important, because I think that's where legislation becomes really critical, because the threshold for dying could cross without the person knowing. And that's why in Paris, quite a few people in the top floor flats actually died in their own houses in 2003. Now, overheating is becoming a problem because, the first time I talked about overheating, I think somebody said, in this country, overheating cannot be an issue. It's all about heating a house, is not overheating. Well, it is a problem because, one, we are building airtight houses, or at least we assume they're airtight. There's reduced infiltration rate. Window openings are becoming insufficient. I think window design is actually not good at the moment. You could have single aspects. There are issues with mechanical ventilation not working. Houses are also becoming smaller. The floor to ceiling height is reducing. So there is less space for stratification of hot air. And this gets worse, it gets exacerbated by a warming climate, where we're expecting temperatures to rise by about 2 to 5 degrees by the middle to end of this century. So this is again an issue that we can't. So there's a new landscape, there are new opportunities, and that's where we operate. It is changing, but I think it's important that it changes. For instance, we need building data. We have to look at indoor air quality, and of course, looking at adaptation and performance of buildings itself. Now, as I said, we have plus 20 projects. I'm not going to talk about them. They are in these areas. I'm going to pick a few of them and talk about it. I'll probably start off with some of our international research, because John had kindly mentioned some of it, and I think it is important that we know what's happening outside of UK, which is important for the UK itself. I worked with the UN to develop this tool called Global Common Carbon Metric, because my PhD was on carbon counting. So, I really wanted to do something to develop a tool where anybody could look at carbon emissions, or, could measure and report carbon emissions of any building in the world. So the tool is very, very, very simple. What it does is that it can measure and report emissions. So you put in your area of the building or area of a city. You tell it whether it's domestic, non-domestic. As soon as you give the location, it looks up the carbon factor and generates indicators like kilowatt hours per square meter per year, and even kilowatt hours per occupant per year. It has been applied widely, about close to 400 square kilometers now, and it's been developed into an ISO standard as I speak. What it does is it provides a consistent way of counting energy use and emissions from buildings, so that we can baseline it and measure improvements against that baseline in a consistent manner. It's very transparent, but it works, and I think that's what is more important for us. As John had mentioned, we use some of this to develop this carbon neutrality standard by BSI, which is now having an improvement as well. And then some years back, I'd done this work for World Bank, which I think is quite relevant today as well. Where I was comparing building stocks of UK, US, and India. And the reason for the three countries is because I'm engaged in the three countries in some shape or form, so I know some of the systems. So UK, as I said, if we compare the countries in terms of their building stocks, 45% of energy use is from buildings in UK, 48% in the US, and 30% in India, and rising. Remember, 30% of households in India don't have electricity. Once they do by 2030, it will be a 6-fold increase. 80% of India is yet to be built. So you're talking about a very big change. To put it in context, I'm talking about 300 million houses which don't have power. So there will be a massive increase there. But if you compare benchmarks, they are not very different. Look at the ones for the school. They're not really that different. That's because of the standards that are being used in India, I think. It's very much the kind of Western-driven standards of probably air-conditioned buildings, which is a little worrying. It needs to be much more indigenous. And then if we look at what's happening in terms of control, and regulatory instruments, I think plenty is happening. The problem is implementation, probably. There's a lot which is there in terms of legislation and voluntary targets as well. But one of the common things I found was that there's a lack of consistent energy and buildings data across the 3 countries. That's common. Even in this country, we don't have good quality energy and buildings data on which to formulate energy policy. It tends to be for policy evaluation, not for policy formulation. So I think it's really important that data collection and analysis is now inbuilt into the systems of countries. I'll come to decorum because that is the foundation of our work. And what really does decorum do? It is a spatial mapping tool. So what I had done in 2005 was to bring 2 quite different fields, energy modeling and spatial mapping together. And the reason I did that was because we wanted to empower cities, local authority planners, energy advisors with a tool by which they could model, measure, map energy use on a house-by-house level. So it doesn't do aggregation. It does aggregation bottom-up, but doesn't do a top-down disaggregation. It's a very bottom-up tool. It evaluates energy use and reductions on a house-by-house level, assesses cost-effectiveness, visualizes this, and sometimes even helps to increase take-up of measures. And to date, we've almost mapped about 5,000 homes in this country, some in the US as well. And primarily what the tool does is you can actually identify hotspots of, let's say the red ones are some of the houses which could take up measures. And then on a house-by-house model, you can run, what can a house do in terms of energy savings and at what cost. But then we've now progressed it quite a bit. This is what can be done, right? The model can also be used to identify what has been done. So we're working with community groups to identify what their baseline is. And with community groups, you have to shift the baseline because their action was taken in the past. And that's been a real interesting experience. So this is one of the community groups we are working with where, we established at pre-2010, so before community action started in an area, these were the average emissions, about 4.5 tons. And then, some improvements happened. These are standard improvements, happening randomly in a community group. An 11% reduction in emissions over 4 years have been retained. So we are able to actually look at that, in terms of what has been done. We can also look at, in terms of what can be done, from there. So we work with community groups to create these community carbon maps. So you can actually see if we did a standard fabric upgrade, depending upon the kind of house, you could save about 10 to 20%. If it was heating system, then you save slightly more, up to maybe 40%. And if you add solar system, then even more. And that can be done at an aggregated level, or you create house archetypes. So people come to us in those community groups, and we can tell them if you're in that house or that kind of house, you could take this kind of action, and these would be the savings, and so much is the cost. So it's quite important to have these tools because they're very visual. We were very surprised because a few years back, a community group in Bicester actually took it up. And what they did was they took the map house by house and contacted 126 householders. 42 of them installed the measures, or they agreed to install the measure. I thought that was a step forward. I hadn't actually visualized it could be done. But mapping has the power of engaging people and bringing them together. And we've now combined that with thermal imaging, both on ground, and we're trying to link it with aerial thermal images as well, and probably satellite data soon. So things are to do retrofit at scale, you need techniques which can be done as well. This is the project which is called Evaluate, which is evaluating low carbon communities. And this is an ESRC, PSRC funded projects with colleagues in Oxford University. And essentially we're working with 6 community groups over the last about 3 years now, evaluating them in terms of their impacts on changing behaviors, effectiveness in terms of bringing how much reductions to happen, and success. And we've adopted action research approach, which means we don't have to just observe them. The subjects can be part of the research, and we can contaminate them, in effect. That's what action research, which is great. Importantly, it actually brings building science and social science, which is difficult, believe me. It was a challenge to understand the language, but now we do. It is much much better in the end, I would say. Difficult to do, but much better results. Including West Oxford. In Oxford, we're working with 6 other community groups, so across the country. We've done a lot of things. I'm not going to go into them, but essentially we've organized 12 focus groups to work with them to understand where they've come from, where they want to be, and what stage they are in. We've organized about 18 community events, from knowledge sharing to show and tell to using arts within a climate change scenario. Various meetings. We've also run energy display libraries and trials. So we've installed some of energy monitors to see whether there is a change in behavior. As you know, every house, every building will have a smart meter in this country in about 8 years. It should have been 6, but it's been postponed a bit. So it's quite important that we look at that. We've carbon mapped about 2,000 houses. We've done a bit of social network analysis to see whom are people talking to, where are the energy discourses happening, and map them. It's quite interesting to see, one house on a street and then how it grows, from there. And then we are doing very detailed monitoring and evaluation, which I'm going to talk about in a bit. But one of the things we did as part of the project was to look at this thing about how far, how much. So we'll talk, many people are talking about evaluation, and it is important. But, if you talk about evaluation, it could be self-reporting, where people just, self-report on their things. To MRV, this is what UN wants for projects which need carbon credits. And it could be a one-off, so it could be a snapshot, to continuous, monitoring. And if you're talking about fabric tests, so if you're looking at thermal images to see heat losses, it could be it could be a snapshot, but it's verified. If you talk about assessment of energy use and user interaction, again that some of the techniques could be continuous, others could be self-reporting. So we have a very mixed methods approach. Looking at remote monitoring, so looking at temperature, humidity, CO2 levels, door window openings within these houses. And also combining that with qualitative analysis, looking at feedback from people and communities themselves. It's important to have a framework, because then you realize how much you're doing and for what purpose and what it will lead to. We want to avoid over-evaluation, certainly, and we also want to avoid survey fatigue. Now I'll show you some of the things that we actually have found. Now, they aren't different, interestingly. These are houses where about standard refurbishment measures have been installed with some low-carbon technologies. So inconsistencies in wall insulation. This house has had cavity wall insulation, but you can see there are inconsistencies. Red is not good. As dark as possible is good. Red shows heat loss. This house did part insulation of one of the rooms, but then the other rooms are now beginning to lose heat. There's a weak link. If we look at, we're working with about 88 houses, out of which 27 houses have had nearly not deep refurbishment, but substantial refurbishments. And we've looked at them over 4 years, and their median change in electricity is about 9%, and the median change in gas use is about 16% reduction. And it is interesting because most of these houses have had either solar PVs or heat pumps. The ones that have heat pumps have actually increased their electricity use a bit, because of course you've shifted the energy vector. Some decrease because of solar PVs as well. So these are quite important things at a substation level, or even at a higher transmission level for electricity use particularly. If you look at, most of these houses have had solar PVs, and what this shows is generation. So the line shows total generation. The bar on the top shows how much is used, so self-consumption of PV, and how much is exported. Now that's quite interesting, because we are in the age of feed-in tariffs. And what we suggest to people is the more you use of what you produce, the better it is, because you're going to, you don't have to buy it at a higher rate. And it depends, on occupancy profiles and other things, of course. And there's a big variation here. So you can see many people are just, exporting most of it, and there's some people who use quite a bit as well. And then that's quite important for demand profiles as well, which I'm not showing. But now when we monitor indoor environmental conditions across these houses, you can see if you look at, for instance, temperature in bedrooms, you can see there's a big variation. It is between, the mean is somewhere between 15 to 20, but the variation is quite high. Some houses are even going above 30 degrees. And the same for living room. And look at what people say, after the refurbishment. Some say, we thought it would feel warmer, But others say they start to notice mold on their ceiling, so there are some unintended consequences. Reasonably good humidity levels, more or less in these houses, but a big variation sometimes. As you know, humidity needs to be between 40 to 70%. Now let's look at attitudes. What happens when people have these systems? Because that's what we want to understand. What is the people interaction with these technologies? So when it's been sunny, I've thought, oh, it's going to be free, so I'll put the tumble dryer on. So that's an unintended consequence. We didn't use a dishwasher for a couple of years, but now we do because we've got the solar PV. There are also positives, of course, not just negatives. But it's important to look at how difficult and challenging it is to change behaviors and then sustain them. I think the point we're trying to make is that if you have these technologies installed, it's very important to also give behavior change guidance alongside as to what needs to be done and followed through as well. And this project actually figures in the community energy strategy. If you've not come across this, there's a national community energy strategy now released. And Everlock is actually one of the exemplar projects within there, and there's a website to look at that. Briefly, I want to touch on some of the low carbon refurbishment work that we've been doing. And this is quite a well-known project. This is in Oxford, it is in Jericho. It achieved above 80% reductions in reality. And the reason it did was because we engaged the user. I'll be very honest with you. All the other technologies were quite similar to what people use. It targeted 16 kilograms CO2, so there was a massive reduction in energy use. I don't think we used out-of-the-world technologies. They're quite simple. Well, people who are involved in this field will find it quite simple. But I think we did them well, and we followed through right from the design stage through construction and in use. And that really helped. Well, the TSB takes this as 80.7% reduction, so that's what we had over the 2 years. Not sure if it will be sustained as 80%, but it was a massive reduction. Remember, this is an R&D project. I'm not saying every house needs to be done like this. It's just an example. The reasonably good environmental conditions. Before the refurbishment, the householders had internal temperatures of 14 degrees. And our models failed because our models were predicting 21. And the reason was there's something called pre-bound effect. If people know that they can't heat their house, they're not going to. People are very intelligent. Whereas, after refurbishment happens, people tend to just, drive up the thermostat a bit. And, before and after occupant perception, they find it warm and comfortable, but they've also lost storage. And I think that's something we have to be very careful when we refurbish these houses, because a lot of kit goes in, and we have to be careful that we don't put a lot of stuff in them so that people lose their basic things. This is another project. This was a 1990s terrace in London. Much difficult to do because the starting point for the previous project was about 80 kilograms CO2 per square meter per year. So I think easier to get to 15 or 16 kilograms. This was 44 kilograms CO2. So this is reasonably done well. It's a 1990s. And I think what we did here, we followed a similar approach, but I think we did some different things. One of which was we had this secure windows inbuilt for climate change adaptation for avoiding overheating. This is a naturally ventilated house and very happy occupants. We put in this ventilated light well to encourage people to dry their clothes. And actually she started to put her baby here. So I expect it's a very comfortable space for her. It's got a lot of breathable insulation as well. It didn't achieve 80%, but did achieve 60%. So I'm not saying 80% is what every house needs to achieve, but there we are. Now, I think the other thing that people might be interested here in knowing is our work on BPE, which is the Building Performance Evaluation. And we have lots of projects. We have about over 15 projects running at any given time. There are a lot of techniques. We can monitor things every minute if we want, and combine that with qualitative and quantitative. But I think what's important is to actually go into the projects, because this is what you will probably like. But I think also be worried, I think, with the results. In fact, be very worried with some of the results. Now, these are all high-performance housing. They are designed to level 4, level 5, so, there's near zero carbon. Quite close. Maybe I shouldn't have named the places where they're located, but anyways. They are by mainstream social housing development. So these are not people who want to really change the world. These are people who are doing this because of code compliance. They're required to do it to get funding. We've been studying some of these houses for 3 years now, right from the design stage. So there's substantial amount of data. This is what the design is. So they were designed to very high air tightness levels, 2, 3, At that time the building regs was 10, so considerably high air tightness. All of them have MVHR systems because they were designed to a very high air tightness level with PVs and everything. Okay, let's compare the design and actual energy use. That's the designed energy use, okay, of these. So we are studying 6 houses across these developments. That's the enhanced model, because remember, models don't count everything. So if you compare a SAP model with actual, it's a wrong comparison because SAP doesn't count everything. You have to improve the SAP by adding lights, appliances, and other things, and cooking energy use, which it doesn't count. So we've added here. And now let's compare it with the real. And you can see some of them differ by a factor of 3. This house, for instance, is no different from average UK dwelling stock. And this is fairly common. This is not something which is special to these houses. There are various reasons. If you convert that into carbon, it gets even worse because electricity is 3 times worse than gas, and most of the houses tend to be electrically heated. So it's a slight increase in electricity means 3 times worse in terms of its carbon impact. So that's where we are. Are we really saving real carbon or virtual carbon? Reasons. Now I'll quickly give you reasons. These are the 6 cases. Firstly, look at what their designed permeability was versus one even fails. One is 15. So that's failed building regs as well, actually. But most of them, interestingly, are in the range of 4 to 6, which makes me think that actually the building industry is maybe at the stage of building to 4 and 6, at which level you don't require mechanical ventilation. So that means these houses have had kit installed, which is not needed, running 24/7, adding to electricity use, which leads to a lot of carbon. So there are lots of interdependencies which are happening here, which need to be considered. Massive issues with ventilation, heat recovery. Look at this duct is not even connected to the terminal. It's this is fairly common. Again, I'm not trying to do building bashing here. I'm just saying that this is fairly common in what we see. So this use, I do not like cold air blowing onto me when I'm sleeping. I'll close the terminal. So effectively, this person has closed the outlet, which means they don't get enough airflow, so they'll open the window, which is also equally good, but that affects the whole balance of the house. Another, user expectations. In warm house, the thermostat is set to 31 degrees, 31, and the windows are open. Again, this is fairly common. This is not unusual. Because I think we are moving to warmer houses where our expectations are increasing phenomenally, and I think it's a case of worry, or is it just habit? Maybe it's just habit. Then if you look at user controls, enough work has been done on usability now to look, to find out that most of the controls don't work. We don't understand them. The system response isn't clear. They aren't accessible. That could be heating controls or ventilation controls. And the same thing happens in non-domestic. So, I can show you buildings after buildings. We have over 50 buildings in this case. So, so these are, interestingly, these are all civic buildings. So I've chosen all buildings where you have a transient population as well. And again, the same thing happens. The difference between design and, actual is phenomenal. And these are the reasons, issues with fabric, issues with, commissioning of stuff. So services and systems are not commissioned properly. BMS and submetering not connected. So the first thing we do in BP studies is connect them. And then you come into user behavior. So plenty has happened before, these things arise. So I'm almost going to end. So few more slides. But before, so there's a lot of stuff to talk about, the difference between design and actual. But there's another thing which is coming our way is overheating. And I've just picked up findings from our research project called SNAC. Without going into the detail, it was a long 3-year project, so I could just talk for another 3 hours on this. But one of the things we found interestingly is until 2050s, in cities such as Oxford, Stockport, and Bristol, you could have passive ventilation depending upon emission scenario you look at. So opening the window and shading the glazing. Again, depends whether your house is south or west or east facing. Most of the homes could be adapted. Most, some may not. Most of it until 2050s. After that, some amount of mechanical, cooling may be required. But until then, it can be done. There are also similarities with mitigation. Again, insulating pipes and other things internally reduces gains. and that's important. Community heating systems in that sense sometimes enhance overheating, so they need to be carefully considered. External insulation, light and color, this used to be very much prevalent in Australia, where you have high albedo effects from external surfaces. And I think, again, that's important. And we need to combine adaptive retrofitting with low carbon retrofitting. This is really, really critical. And I think one of the big impacts of the project, it finished in 2012, so end of 2012, so it's been a year, was we created these maps for overheating one. So we looked at 6 neighborhoods across the 3 cities, and created maps of which houses would overheat, in 2030s, 50s, and 80s. And then what could be done? So the green ones are the ones which could be adapted. The red ones are which can't be adapted, for various reasons. But interestingly, it actually, formed the evidence for, the government's work on overheating in homes. This led to the National Adaptation Program, where this project figures. So the evidence has been taken up. A lot of research has been written into scientific papers. And I think that's really important. But I think for me, the most important thing was that it informed a little bit about Green Deal. One of the things we got in was that with Green Deal assessments, there is no overheating risk analysis done. And at least the assessors should be trained in identifying overheating risks. Because what you don't want to do is solve one problem at the cost of the other. And that's, I think, quite important for us. So I think it has had some impact in that sense. So now, final thoughts, before I end. Where are we, heading to? One of the things we've been working on is combining, mapping, which is, what is very close to my heart, of course, with monitoring and seeing whether we can develop a kind of an approach which can be urban scale and also house by house, because one size doesn't fit all. So let's say, one creates a decorum map, identifies hotspots. Retrofitting is done. Let's say a whole street is retrofitted. Some amount of post-retrofit analysis is done, to understand whether it's, actually performing. It's fed back into the model, so the model improves itself, and it becomes like a knowledge management system. We call it a community-scale retrofit or a community-led retrofit. But then there'll be some people who would want to do a whole house retrofit, and they should do that, which could be done by, and that would mean that an analysis is done prior to retrofitting, so a detailed pre-retrofit, survey in-use characteristics, both of occupants and the dwelling, are assessed. It feeds into the model at this stage, actually, because it improves the predictions straight away. And after the retrofit is done, again, there's a detailed monitoring analysis done, and it feeds into the model, so that this becomes like a management system for improving buildings. And that we call as a deep retrofit approach. Some people call it advanced retrofit as well. The second thing that we've been really struggling with, and I think we are about to publish this, is a protocol for building performance evaluation. We've moved from no evaluation to a lot of evaluation, and I'm very passionate about differentiating between need to know versus nice to have, and avoiding over-evaluation survey fatigue. So we've developed this protocol of what needs to be done for existing buildings, what should be studied, and what should be studied for new buildings and refurbishments, let's say, and at what stage. So what is really, really critical, and at a basic level, so what you could do for all the buildings, let's say, which are improved, at a core level, so a little bit of detail, maybe 10 houses out of a development of 50. 3 is a comprehensive, so maybe this is done for relatively fewer houses where innovation is happening in terms of materiality or technologies. And then advanced, maybe for the prototype buildings, which is done right from the design stage and taken through. So the fabric is studied in detail, the design and construction audit is studied, substantiated by monitoring, interviews, and analysis. This is about to be published, but I think we need a kind of a protocol to understand this. What is essential and what isn't. The third thing that I think we've been working on, which I think is quite important, because it brings, probably for the first time, people and energy data together. We've got a project through the TSB Future Cities Solutions Competition to design or develop open source data platform for energy and buildings. That is all of what we had to do. But what we've done is we've developed user profiles, because we feel different user groups in cities have different tools that they want and different motivations that they have. So we started off by saying that we'll develop a tool for cities to be able to measure and report, energy use from buildings and take action. That still stays, but we've added another stream which says it's got to be an engagement tool. So, the householders themselves can upload data. They can actually see how their house is performing against others. So they can either see it as a number, as a map, or they can track it over time in almost real time. And then what we've done is added a functionality called a retrofit brokerage function. Given that we are in a state of inertia with retrofit, it brings householders who want their houses to be retrofitted can put them up on the platform, and then there are retrofit providers who can contact them, and all of this is moderated by the local authority. So it's a much more interactive platform. It's still being developed, so there is a prototype if somebody wants to use it. But we think this could be a game changer, because this suddenly makes data more relevant, which I think is important. And I think before I end, I just want to talk about one thing which I had done over last year, or maybe the year before last, which was looking at what are we doing in terms of next 40 years in terms of energy and housing research or energy and building research. And this had a good launch in UCL and other places as to what should we do. And one of the things I had said clearly was it's actually about collaboration going forward, not just competition. Universities compete against each other to win grants, and that's fine. But I think it's more about collaboration now, because the scale of the work that needs to be done is a lot bigger. We need whole systems thinking, because there are interdependencies. By not having the right information through your handover, you're not going to understand the controls and operate the windows wrongly and use the MVHR wrongly, which will affect energy use. So that's not occupant behavior. That's got interdependencies. And I think these are really important things when we talk about, interdisciplinary whole systems thinking approach. I think active engagement is required with various kinds of communities, not just communities of place, by which I mean local authorities or community groups, also communities of practice, also communities of interest, people, us, who are interested in it. And that's important for a reality check as well, whether, what we're doing is useful. And I think, as I said before, we need to make sure that research forms the basis for policy, not for policy evaluation. And so that we can make sure that there's a critical mass of researchers who are sustained over a longer period of time, so that we can deliver this level of research. Thank you for your attention, and thank you to my group.